Okay, let's move on to the next part. We are now going to set ourselves for computing the fastener stiffness, and this calculation is important because it will actually feed into the loads which are carried by different members. And once you know the loads carried by different members, that is just, there's not one thing here. There's the screw itself, but then there's the members which are shown in green, which are actually compressed. So forces when you apply are going to be distributed across the fastener and the members, and you need to know what the distribution is. If you don't know what the force distribution is, you cannot compute stress, and then you cannot compute the factor of safety. There's another complication here, which is you can see that the members, they can be of different materials. So that actually creates some complications. You could also have a case where the screws are not fully threaded. So here I've shown both these screws are fully threaded, but there could be screws which are not fully threaded, in which case you need to account for that. So there's a lot going on here, which we'll hopefully tackle in this part. It'll actually give us a way to compute the forces if you know the stiffness. So stiffness and force are directly proportional, right? Force is K times, or stiffness times the deflection. Okay, so here are three ways, possible ways in which you could have fasteners coming in. You could have a through hole. So you can see that the hole is going all over to the two members. You put a nut, you put a screw. The screw and the threaded part is one item, right? And then the nut is a separate piece. You put it together. You could have a blind hole, which there is no through hole. And then you could also have what is known as a stud. So this is kind of interesting. This stud actually sits inside the second member. Let's call that member 2. It is a permanent thing. It just sits there. And then once, all you have to do now is to screw in this nut. This is actually a nut. So studs are permanent, while screws are not permanent. So this just goes through the details. So it is, the main thing is that it is permanent. So nut and washer, which actually there is a washer here, which I should have talked about, which is used, which basically is something which you can remove. Okay, so we'll get to the details of the stresses in just a bit, but here's something to know is when you put in the screw and you start tightening the nut, what happens is that the screw is stretched. Okay. Why it's stretched? Because what's happening is the act of putting that nut inside causes the screw to elongate. The members, on the other hand, are compressed. So it's compressive force on the members, but there's an actual stretching force on the screw, tension force. So we'll talk about this pre-tension and I will come back again, but just an introduction. Okay, so when you have a screw, so here's a setup where you have a screw which is partly threaded, partly unthreaded, okay? And it has two members, which I've shown there. In order to compute the stiffness, I'll just review something you've probably done a long time back. We have springs in series. So when springs are in series, so a setup like this, K1, K2, you might have learned about this in what is that, vibrations class?
Vibrations 308, and we also learned about it in 347.
347, okay. Okay, springs in series. This is like a quick derivation. When springs are in series, the same forces are applied to both the springs. However, the deflections add up. So the net deflection is delta 1 plus delta 2, which is the deflection of those springs. So delta 1 is F divided by K1, and delta 2 is F divided by K2. Because the forces are the same, you can do some math and simplify this, and the equivalent stiffness for springs in series is this thing, K1, K2 divided by K1 plus K2. Okay, the other thing which is going to be useful is that stress-strain relationship. Stress is E times epsilon. Stress is P divided by A. Strain is delta divided by L. You can simplify this and compute deflection, so you have deflection and your force, what remains here has to be the K, right? Because this looks like delta equals force divided by stiffness. So this is another formula which I'm sure you've seen this in some form. And we've also seen this long time back. We really identified it as K, but that's a spring stiffness right there. So you can think when you do a compression tension experiment, you actually can think of it in terms of a spring. Okay, now that we have that, let's look at how to compute the effective stiffness of something of a screw which has unthreaded. This is the unthreaded. I think I used the notation D. And this is the threaded T. So when you have D and T, and it's subjected to a force, this is exactly like springs in series, right? K1, K2 subjected to a force F. Okay, so that's that. So springs in series. So if you have the spring constants are KT, KD, and KT, then you can use the formula KT times KD, KT plus KD. That's the first part. The second part is each of these KT and KD can be written in terms of, we just derived the formula AE divided by L. Right? AE divided by L. So K is AE divided by L. That basically goes in here. So here we can compute the net effective stiffness as AT, AD, E divided by the summation of AT, A and L. Okay, so this is what you will do if you see a screw with two different screw which has threads and no threads. If, however, if you can approximate the screw to have only no threads, which is very rare, or really you cannot have a screw without threads, but if the threaded part is really small, okay, if it's very small, then it doesn't really affect the stiffness. You can neglect KT and you get K effective is just KD, AD, E divided by L. Okay, so you can neglect KT. You can never have an unthreaded screw, then it's not a screw, it's something else. If you have a fully threaded screw or you have the threaded portion, unthreaded portion is small, then you can just ignore the KD. So ignore, neglect, or just don't take into consideration KD, and you have KT is K effective ATE by LT. So that's straightforward. Okay, so now what we've done is we've actually done only this part, which is the fastener stiffness, which is basically analyzing springs in series. Okay, now we come to the sort of the harder part, which is how do you compute the stiffness of the members? The members is something which holds on to the screw through compressive force. Okay, the member is shown there. We already computed stiffness of this. It turns out there's some theory which we'll be using to compute the stresses in a member. It's called pressure cone approach or conical frusta. It's basically what this whole thing is. Okay, I've written down a few things, but the key idea here is that it's actually over here. So for a second, don't read everything as there's a lot of details which you can read later. What they found is that when you compress members by using a screw in the way shown, then the stress can be approximated to follow a so-called conical frusta. That means that the stress can be approximated with this cone-shaped objects, which means that the stress is no longer going to be, you cannot assume that stress is like, usually when we take stresses in a cylinder, we assume that the stress is going to be over that area. But when you're doing the members, experiments have found that you need to approximate the area as a frusta, which has an increasing taper. Okay, that's just from experiment. It's not something which I don't know if there's a theory for that. Okay, so it's an empirical finding. They probably measured the stresses as a function of distance and width, and they found that That is a good approximation. So you can see that the frustra, it's basically something like this. So you can see this L divided by 2, that's the top half, and then there'll be a bottom half. Okay. So what is done is there is this angle alpha, which is a free parameter, and also found experimentally that a value of 30 degrees gives a good approximation for the stresses. Again, an empirical thing, nothing to do with any physics-based theory, or maybe there is, but I don't know about. Okay, so then in order to compute the stiffness of this part, what you do is you use the same expression as we used before. What is this expression? It's basically delta equals P divided by AE divided by L, or P divided by K, right? Remember, it comes from the stress-strain relationship. So what is done is this is P for you, this is E, it's E is as it is. There is A, which is actually a function of X. Why it's a function of X? Because X is the distance from the top, and you can see the area is increasing. So you need to assume that, otherwise, if A was constant, then you just put A, which becomes this formula, but A is a function of X, and then dx is this L is dx. So this L is dx, and this A is A of function of X. Now, we have to find the area. This is going to be the area, this is going to be the inner diameter, and then there is a outer diameter, which is a ring like this. So the inner diameter is, just draw this. So that's the inner one, D, and then the outer one sits Sue's green. So that's the outer one, which is actually a function of X. So that's D0. So here is a value for D0 based on that. You can use similar triangles and do it. That's not important, but you take A of X, you put it in there, and you get, you need to integrate over this length, 0 to T. It's a complex integral. I don't want you to do it. But what comes out of this is that Ki, which is, Ki is the ratio of P divided by delta. So you need to divide this and figure out what Ki is. Here, Ki is P divided by delta. It comes out to be this very complicated looking expression. Pi ED tan alpha, this is the natural log. So when you're using your calculator, you need to use the one which says ln, I think, right? Do not use log, because I think it's usually the base 10. This is not what it is. It's the natural log, log to the base E. Okay. Okay. So we have Ki, and this is a function of, you can see, T, E, D, and so on. Now we said specifically that alpha is 30 degrees. So we can actually put alpha as 30 degrees. That just makes it slightly simple, I guess, to look at. But that's the expression we'll be using. So if you want to save this, you want to just store it for alpha equals 30. I don't think I will ask you any other value. Okay. Now, if you have multiple members, so K1, K2, K3, all these members are, as you can see, in series, right? So this is like K1, K2, K3, and so on till Ki. So if all you do is, the expression you want to use is probably this one, because the other one becomes a little bit more complicated to use. So, but use this one, the reciprocal, in order to compute that. Okay, so springs in series. Now, okay, one last thing, and then we will get to the problem. Okay. These are just special cases of that formula. So let's read through. This will just make your life easy when you're doing the calculations. So let's assume that members 1 and 2, so 1 and 2 is drawn here, have the same Young's modulus E. So they are made of the same material. They also have same back-to-back cones, which means that the cone, which is I was talking about, is something like this. So that cone is identical back-to-back and of length of 2t. The washer diameter is dw. So if you have 1 and 2 of the same material, they have the same stiffness, they have the same cone, they're very symmetric, you can just say that the net K is using this formula, K times K divided by K plus K, which comes out to be K divided by 2. So the net stiffness is going to be half of the stiffness of any one of them. Okay, so that's that. Now this is just taking this formula, which I wrote down earlier, and just putting that 2 in there. That's it. There's nothing different than just that 2. Okay, so it's up to you if you want to copy this in your notes, but this is just changing it by half. That's it. For standard hexagon head bolts, so this is something again found empirically, that if you have hexagon head bolts and cap screws, then they know something about the washer diameter. TW is washer diameter. So they're going to substitute the washer diameter here with 1.5D. That will just simplify the expression. So there's no dW or washer diameter anymore because it's been replaced. Okay, yeah, question. The bolt, we did it separately. So the bolt comes, that's the bolt, fastener stiffness. That was calculated over here. Wait, I'll show you. That's the bolt. The bolt things will come here. And then the fastener will come. This is just a fastener. Now, okay, so far in this section, I've not put both things together. So when you have a bolt and fastener, those things actually in parallel. So if you see this, this and this is in parallel. It's almost like K bolt, K member. Okay, and there is a way to analyze. There is more stuff coming next week where I'll show you how to analyze something in parallel and then the factor of safety and so on. So we're just trying to understand individually member stiffness and this, and then we'll eventually put it all together. Okay, so here is a problem which sort of goes through how do you compute the stiffness of the bolt and the stiffness of the members. There are two members here, the light gray and the dark gray. Okay, and also, what if the dark gray and light gray were different, had different materials? How do you do that calculation? So that also is covered here. Okay, we have some time. Let's get started with this. Okay, so what I'll do is I'll try to do the first part, which is the straightforward one. The B and C will take me some time. You have to use the frustra method, the pyramid method, the cone method. So let's just do the first part and then we'll worry about this B and C next time. And we can go a little early. Okay, so here is, okay, the fastener member dimension shown below is for the untightened configuration. That's key. So this is just, it's been set there. Now it's not been tightened. Okay, when you tighten, things will change a little bit. Compute the following. The bolt spring rate, assume the bolt is made of steel, and in the clamp state, LT is 1.095, LD is 0.125, AT is 0.1599 inch square. So I have given you everything you need to compute this, but normally you would have to compute this from a table, which I'm skipping here, but there is, it comes basically from looking at a table, which could come from manufacturer or standard tables for these dimensions. So let's just compute the bolt spring rate. Okay, so you can see that the bolt has two parts to it. there is the threaded part and the unthreaded part, and that's why you need to uh, use the springs in series formula. So here is, let's do part A. I'm just going to draw the bolt, and you can see the bolt, the top part is unthreaded, bottom part is threaded. Let's draw some threads. So this part is LT, this part is LD, and then the formula for bolt stiffness for parts in series is AD AT E divided by AD LT plus AT LD. Okay, so just copy it, paste it from there. We are told that E is 30 times 10 raised to 6. AD, what's given? It's LT is given. Let's write what is given first. LT is 1.095 inch square. LD is 0.25 inch. Again, this is, sorry, not inch square. This is all given, 0.25, and AD is 0.1599. Okay, so we need to compute AD. What's AD? A is the diameter of this part, but I think we know the diameter of, do we know the diameter of the bolt? Yeah, it's given here. Diameter of the bolt is 0.5 inch, so which means that this is D is 0.5 inch. So all we need to do is use the formula pi d squared divided by 4, 0.1963. So if you see this expression KB, everything is known. I've put it all down. So KB comes out to be, if you want, I can write this down, 0.1963. AT is 0.1599. E is 30 times 10 raised to 6 divided by ATLT. AT, okay, just be careful. This is 80 times AD times LT, not AD times LD. AD times LT, 1.095 plus AT. AT is 0.1599. LD is 0.25. Okay, everything in there. KB comes out to be 3.69 times 10 raised to 6 pound force per inch. Okay, here's a simplified figure. Okay, so that's my bolt. Here is member 1, member 2, bottom member, and I'll just shade this so you know it's the same object. So this is my bolt. Okay, so here is actually the figure is given here. I'm just redrawing this. A part of it is threaded, part of it is not. Uh, we're given the thicknesses of the washer, the top plate, which is half, and 3/4 of the bottom plate. Let me just draw those. This is 3/4, 0.5, And then this thing is 0.095. Okay, so the total length is 0.095 plus 0.5 plus 3/4. So this comes out to be 1.345. Okay, and to compute this thickness T, or the height for the first star, we always take the half of that. So the T, remember, is, if you see this figure, T is basically this distance from here to here. So that is equally divided. So half of L, so it is 0.6725. So now that we've got T, now let's redraw this figure with the cones. Okay, so the same figure with the cones. Copy. Okay, so the distance from, so this is 3/4. 3/4 is what? 0.75. So we know that this much is going to be probably be 0.6725. So it doesn't really go all the way to the top, the bottom member. There's some gap left. So that's the important part. And this is 0.6725. Okay, and something about the material, we know that this material is gray cast iron. Okay, so material here. And then we know that the top material is steel. So this part is steel. It turns out that the washer is also, or the bolt, assume the washer and the top member are made of steel. So that's actually very important. So these two members have the same material. Okay, so that this, let's put a legend here. This is steel, and this is gray cast iron. Okay, now that we have that, here is how to think about this in terms of the cones. Okay, let's pay attention. So the thickness is given here, 0.6725. It's approximately here, right? It's not, it's sort of buried inside. The tip is going to be buried inside the second member, that is the largest part of the cone. So it'll be something like this. And then it'll taper down like this. It's always symmetric. So whatever this is this is just the same thing. Okay, we can actually compute what this additional distance is. So this distance. So this distance is basically 0.75 minus 0.6725, because you can see it's 0.75 for the height minus 0.6725 is the thickness T. It comes out to be 0.0775. Okay, so the point of doing all this exercise is that there are basically, for analysis, we need to not take two stiffnesses, but there are three stiffnesses involved. The first stiffness is of the steel washer and the top plate. Because they are made of the same material, you can take them as one and find the first stiffness. The second stiffness is because of that small part which is of length 0.0775. It's actually buried in the gray cast iron. So that has different, well, it has a different material, but it is a part of the first cone. So you need to include that slightly differently from the third part, which I'll talk about next. So the third one is actually the gray cast iron, which sits in the bottom half. So there are three springs constants. Okay. So K1 would be steel washer plus member 1. K2 would be the cast iron uh, for member 2 of thickness equals 0.0775. And the third one is cast iron member 2 of thickness 0.6725. So these two are part of cone 1, as you can see, and this is part of cone 2. Because this is part of cone 1 and not part of cone 2, you cannot combine them. So everything which is in a single cone has to be taken together, it has to be analyzed independently. If there's a material change, like there is a material change between K1 and K2, you need to take a different stiffness. So once you get K1, K2, K3, then it's fairly straightforward. You say that 1 km is 1 divided by K1 plus 1 divided by K2 plus 1 divided by K3. This is the springs in parallel. Parallel springs. Okay, so that's the sort of the overview of what we're going to do. We're going to find K1, K2, K3. The last step is super simple. Let's compute K1 first, okay? Okay, so I'm going to just take this figure and use it 3 times. Do this slowly so you can understand what's going on. So K1. Okay, so the formula we're going to use for all these cases is, I just showed that to you. It was this one. This formula requires E, lowercase, uppercase d, and t. So let's take this. Okay, so we'll need this 3 times. So I'm just going to copy it, save it 3 times. 30, 10 raised to 6. Okay, next we have to get thickness. So thickness, we know it is 0.6725, but then you need to subtract out 0.0775. So that would be 0.6725 minus 0.0775 comes out to be 0.595. So this distance okay. Next is small d. This lowercase d is actually the diameter of the bolt. That is probably given to us. Maybe it's, yeah, there it is. Diameter of the bolt is 0.5 inches, and the diameter of the washer is 0.75. So this is 0.5, while this is 0.75. So 0.5 is d, small upper lowercase d. Okay, and we need to compute d. Now, what is d? If you look at the figure, so this is probably the hardest one to compute d. If you go back to, what is that? Okay, slightly a mess. Okay, we just need to figure out. So this cone starts somewhere we need to figure out the diameter of the topmost part of the cone. That's all. So here it is this. So that's uppercase D. So we know what that is. If you go back to the figure, this part is D 0.75. That's the diameter of the washer. This is diameter of bolt. And this value is for steel. Okay, so everything in there is known. Right? We'll use this formula. Okay, I'm just going to write the value, but you can use that formula. Everything is known. We can, or we've determined everything needed there. This comes to be 30.8 times 10 raised to 6 pound force per inch. Okay, that's part one. Now, let's go to the next one. This one is probably the most involved one. We need to now compute K2 for, so K1 is for just this part. Let's do K2. Okay, K2 will be this part. Okay, the thing which is sandwiched between the blue and the pink, but it's part of pink. Okay, so again, we need to figure out all these things over here. This is cast iron now, it's pink. So the cast iron stiffness is 14.5 times 10 to 6. It's given in the problem. So this is cast iron. Okay, next is the thickness. So we've already computed that it's 0.0775. This is the thickness. Okay, small d or lowercase d is always the diameter of the bolt. It is 0.5. Okay. Now this is the part which is the not the involved, but the one which we might have to work. This is going to give me the diameter of, if you go back and see what this d is in this expression, it's always the top part of the cone, right? The top part for this question is going to be, this is the top part where the cone starts. So this is a separate cone which is buried inside the pink one, the way it is shown. Okay, the way you figure this out is through that angle alpha. It's basically a 30 degrees angle, and then somewhere here, let's say we have a t. This distance is 0.075 or 0.775. So it's basically using similar triangles. So we need something else, another dimension to get it. So we kind of know this 0.6725. Actually, we know this much, 0.595. And I think we also know the distance from here to here. It is the diameter of the washer. Okay, so 0.75 is this. This is D, the unknown. And then we know that angle is 30 degrees. Okay, so you could use similar triangles, or I'm going to give you really a formula to do this. For similar triangles, you'll have to identify this distance first, and then use triangles, because then you can use the similar triangles formula. But here's a easy way to figure that out. It is this formula. It's always the diameter, any diameter will do. Doesn't matter if it is this or something else, provided you know the distance of this diameter from uh, the part where you are trying to analyze. So the height here is what is x, and then tan of alpha. So this is basically a formula which comes from the similar triangles, just as a simplified. You can check by drawing similar triangles. So 0.75, I should make this small d for the diameter. X is 0.595, tan of 30 degrees. Okay, so with this, you get 1.437. Okay, so again, in the formula over here, E is known, uppercase D, lowercase d is known, thickness is known. So we just have to now solve for K2. Comes out to be 285.5, 10 raised to 6 lbf per inch. Okay, so that's K2. Let's do K3, which is the pink part buried inside the second member. Okay, so K3 would be this. Okay, again, we do the same thing. We need to identify all these, the four variables. A is gray cast iron, so 14.5 raised to 10 raised to 6 psi. psi. Yeah. A psi. No, just psi. So that's gray cast iron. Okay, next piece is the bolt diameter, which is fairly straightforward. This is just always the bolt diameter. Given. Next is the thickness. So here, thickness is going to be this one. Basically, it starts over here, ends over there. So it's 0.6725 inch. Okay, now the third part is uppercase D. Okay, this is where it gets tricky. How do you find uppercase D? Is it this? The answer is no, it's not. It's always the top part of the cone. So it's always the top part. That's the top part. But we know what this is. This part is the same as the diameter of the washer, 0.75. So you always go, when you're computing this D, you always go from the top of the, whatever that is surface, you go from top to the bottom, not from the bottom to the top. So if you use this distance, it's going to be incorrect, because then you're at the bottom of the cone. Okay, so D is 0.75. And now we have everything we need to solve for K3. And we know everything in the formula, right? Everything is known. So we can solve for K3. So K3 comes out to be 14. 15 lbf per inch. And now that we've got all the three, we can compute Km is 1 divided by K1 plus 1 divided by K2 plus 1 divided by K3, which is 1 divided by 30.8 plus 285.5 plus 14.15, and then the whole thing is 10 raised to negative 6. So Km comes out to be 9.738. I don't know if you remember this fact from springs in series, but the net spring constant is always a value lower than the worst case. Yeah, question. Sure, but I post all these. This is not like you'll get this. This will be posted on Blackboard.
Yeah.
Sure.
One test right now.
Oh, okay, go ahead. This one, you want to take a photo?
Yeah, I got it.
You got it, okay. Okay, so Km is this. You can see that it is actually less than the lowest one. That's always true. If you have springs in series, they always give you a stiffness which is less than the stiffness of all taken together. Okay, we are still not done with this question. We have a part C. Member spring rate, assuming the washer, top, and bottom members are made of steel. Now here, we assume that the washer, the top part, the pop part, and the bottom part are made of the same material, steel. So in this case, now suddenly life becomes much, much simple because you can just use the fact that they have the same material to basically think of them as two springs in series. So for part C, what it looks like is something like this. You know what? I'll just copy the figure. I can just repurpose that figure. Okay, so we don't really need this. We don't have this. We don't have to worry about this. Both of them are made of the same material. So here is everything is of steel. So this is steel. Now the frusta is going to be like this. Just be mindful that it should end here. Okay, so the thickness of the frusta is T. If this is member K1 and this is K2, this is the, or rather, we not do it that way. Okay, so each cone, each cone has stiffness K. So net stiffness is Km equals K divided by 2. So we only need to find, in other words, the stiffness of one of those of height 0.6725. So the formula here is the same formula as before. So I'm going to copy the same one, but I just need to do it once for one of them, top one or bottom one. So in this formula, what we'll do is we'll put E is 30, 10 raised to 6. This is for steel. D is still 0.5 diameter of bolt. T is simply 0.6725. We're only considering one and then just taking the half, right? And then uppercase D is just Wait, this is not right. This is D. So D is the diameter of washer, which is 0.75. Okay, so putting all these values, we get K equals so Km equals half of K. So K comes from there. You can put it here and then take the half. Is 14.64 pound force per inch. Okay, so pretty complicated, but that's the